Okay, welcome students to this another session on industrial metallurgy. Let us see what we are going to discuss in this session. This is session number 8, and these are the contents that we shall try to finish in this particular session. So in the last session, I was to discuss with you that what is the significance of the phases which are present in the microstructure of a material. Basically, the point of discussion is that industrial metallurgy works on the principle that we would be able to improve upon the mechanical properties of a material system, because mechanical properties of any metal or an alloy system are completely dependent on its microstructure. And if we want to change the properties, we have to change the microstructure. We also saw in earlier sessions that microstructure has got two main constituents. One is the grain size, and the other is the type, the number, and the other details of the phases that are present in the microstructure. In the last session, I said that grain size as well as phase details both make an effect on the microstructure and hence the mechanical properties. If there is any change, if any change takes place in the grain size or in the phase details or in both, that changes the microstructure, and that change in the microstructure brings about a change in the mechanical properties. What we need to understand is point number one: what type of microstructure gives what type of mechanical properties. And after having gained that knowledge that what type of microstructure gives or can give what type of mechanical properties, we need to understand and know how do we get a particular type of a microstructure. So the bottom line is that in industrial metallurgy, you need to know what type of mechanical properties are you wishing to be there in a metal or an alloy system, and then what type of microstructure can bring those properties, and finally with what processing I get that type of a microstructure into the material system. So if you know these things, you have total control over the mechanical properties of a materials system. So now in this session particularly, we are going to see that when in a given materials microstructure some phases with some phase details are present, how do they affect the mechanical properties of that metal or an alloy system? Okay, so I said in the last part of the last session that if you talk about that how do phases affect the mechanical properties of a material system, you see whenever you look into the microstructure of a material, you would find that generally, most generally, there is one phase which is dominating the microstructure, means that is present, that is occupying most of the space, most of the area in the microstructure of the material. And we say we talk about this area or space in terms of the volume fraction which the phase is occupying. So whenever you look into the microstructure of any metal or an alloy system, most generally you'll find that there is some specific phase which has occupied maximum volume fraction in the microstructure of that material. This phase forms the background of the microstructure. This phase is continuously present everywhere in the microstructure of the material. So this phase is called the primary phase, the continuous phase, or the background phase. There might not be any other phase present in the material system. There may be one phase present in the material system. There may be 15 other phases present in the material system's microstructure. But whatsoever other phases are present, all those would be termed as the secondary phase or the secondary phases. Mind it, continuous phase and secondary phase both would affect the properties of a material system because of their presence in the microstructure. But researchers have now gather this information that the way how these phases affect the properties of a material system is different. The continuous phase is that phase which occupies maximum volume fraction, and this phase affects the properties of a material system by virtue of its volume fraction. So if the volume fraction is 99% and if its volume fraction is 60%, its effect would be different on the properties. On the contrary, the secondary phases do not have that much of a volume fraction in a material system, so they do not largely affect the properties of a material systems by their volume fraction. Rather, they affect the properties of a material system by virtue of their shape, by virtue of their size, by virtue of the way they are distributed in the primary phase, which is called the morphology. So secondary phases affect the properties of a material system by virtue of their morphology. Okay, so this I've already explained, that the phase which occupies maximum area or volume fraction in a material system's microstructure is called its primary phase, background phase, or continuous phase. Now, this also has been found after a lot of research that though every phase present in the material systems microstructure would affect every of its mechanical properties, but there's a slight difference. The continuous phase, the primary phase, would affect more properties like the strength, properties like the hardness, properties like the ductility. On the contrary, properties like machinability, hardenability, impact strength, etc., would be more affected by the secondary phase and not by the continuous phase. Okay. Then whatsoever properties are affected by, you said that continuous phase or primary phase or background phase affects these properties. Okay, understood. But how does it affect these properties? It affects these properties by its volume fraction. Okay, then we come to the secondary phase. The secondary phase are the phases which do not occupy the maximum volume fraction. So these phases are called secondary phases, or they are also called the discontinuous phases. Okay, how do they affect the what properties do they affect? They affect properties like machinability, impact strength. There is another very important characteristic, hardenability, which we'll discuss in the lectures to come. And how does the secondary phases affect the properties of a material system? The secondary phases affect the properties of the material system in which they are present through their shape, through their size, through their distribution, that is through their morphology. And what are the properties which they largely affect? Which are mentioned in this third bullet point. Now, students, let's explain all this with the help of an example. I have taken a plain carbon steel sample, and that plain carbon steel sample most generally will have these two phases in the microstructure of a material. One of the phases is ferrite, the other phase is cementite. What we can see is this white region or this white area is being referred to as the primary phase. It occupies maximum volume fraction. It has occupied 98% of the area that you can see in the microstructure. So this becomes the primary phase. The other phase is cementite, remaining 100 minus 98, 2% is occupied by cementite. Then cementite has got this thin plate type of a morphology. Okay, now before I move on to explain as to how each of these phases would affect the properties of a of this typical steel, what I need to understand is every phase, whether it's ferrite or austenite or martensite or cementite, every phase has got its unique set of mechanical properties. So ferrite has got its own unique set of mechanical properties, cementite has got its own unique set of mechanical properties. Now, what did I say in the last slide? I said that the primary phase affects properties like strength, hardness, ductility. And how does it affect those properties? It affects those properties by virtue of its volume fraction. What do I mean to say by that? I mean to say by that for a moment, if you assume that this steel was only containing ferrite in it, so the volume fraction of ferrite would have been 100%. Now, if the volume fraction of ferrite is 100%, that means the ferrite, whatsoever properties it possesses, the same properties would be of the material system. For example, I know that ferrite has got a tensile strength of about 235 megapascals. It has got a hardness of about 30 HRB. it has got a ductility over a gauge length of 5 centimeter, about 50%. So if ferrite has got 50% ductility, 235 megapascal tensile strength, 30 HRB hardness, if this typical steel was containing 100% ferrite in it, ferrite would have given the same properties to the steel also. The steel also would have been having a tensile strength of 235 megapascals, 30 HB hardness, and 50% ductility. But now the primary phase is having 98. So 98% means largely the strength, ductility, and hardness values would be similar to that are of ferrite. The remaining would be influenced by this cementite. Now let's come on to the next properties, like impact strength is there, hardenability is there, machinability is there. Now those properties would be governed more by the cementite phase, but so that does not mean that they would not be governed by ferrite. But the larger influence, the more domineering influence, the more significant influence would be of the secondary phase, that is cementite. Now cementite, if you see over here, is present in this thin plate-like form. So if somebody asks you that what is going to be the impact strength of this material, see, the impact strength of this material would be poor. Why? When the shock load would come onto this material, whatsoever shock load comes onto these thin cementite plates, because they do not have any large bearing area to hold that shock load, they'll immediately have a crack in them. Crack initiation and propagation would happen, and the material would flow. Means the shock will not be able to be transmitted from here to this portion. On the contrary, if the cementite morphology was, say, globular or was of bigger size, so that it had ample of cross-sectional area to bear the shock load, then easily it would have transferred the load from it to the primary phase before failure could have happened. Similarly, we'll talk about machinability by some other example. Okay, now in this case, see, when we discuss about machinability, see, when the cutting tool starts cutting the material, it is these dislocations that start moving. Ferrite, when they are moving in ferrite phase, they are not having any problem. But when this hard cementite phase comes in between, because it's in the lamellar form, the cutting tool will get blunt over here. So when you have this typical lamellar type of a microstructure, machinability of a material is never good. Even if you talk about hardness, the shape is lamellar, but still bearing area of the secondary phase is not great. So when the shock load would come, a large stress concentration would take place on this cementite, and again the cementite phase will develop cracks in it, which would initiate and which would propagate and would lead to failure of the material. Now, if we talk about machinability, which is largely dependent upon the secondary phase, and I said secondary phase affects the properties by virtue of its morphology. Now, in order that these dislocations move and machinability becomes excellent, I have to do away with this lamellar type of morphology of the secondary phase. So we give a heat treatment called spheroidization annealing. And when that heat treatment is given, the lamellar cementite transforms to this type of a globular cementite. So when you start cutting now, you see on majority of the instances, these dislocations bypass the secondary phase. The machinability becomes very, very good. So students, I hope you have broadly understood that how do primary phase, secondary phase, means in totality, how do phases affect the mechanical properties of a material system. We'll continue to do these things in larger detail as the lectures proceed, and this session was only to give you a very basic idea as to how microstructure and hence phases affect the properties of a material system. Thanks for watching. Thank you so much.